we generate a carbon ion, and after a while, the leaving group is departing. Okay? The first option is called E2, and we will see why is E2. The second option is called E1, and the third option is called E1 CB. Okay? These are the names, and now we will check one by one how this is working. We will start with the E2. Remember E2? The base is taking the proton. At the same time, then the leaving group is departing. Okay, and remember that R could be a hydrogen, could be a proton, could be a hydrogen, could be a carbon, everything could be. Okay? That means what is happening is that the base is coming, the base is taking the hydrogen, the pair of electrons that are forming the carbon-hydrogen bond are forming the double bond, and the leaving group is departing. What we have is basically plus. Okay? Now, why I draw it in this way? This is important. Because the E2, in order that happens, we have a transition state, because all happens in only one step. Okay? We have a transition state. And this transition state must be anti-periplanar. And what means anti-periplanar? Anti-periplanar means that the dihedral angle between X, the leaving group, and the hydrogen must be 180 degrees. Okay? In easy words, the hydrogen is going down, the leaving group is going up. Or just the opposite, the leaving group is going down and the hydrogen is going up. You need to draw this conformation, okay? In order that happens. We will put an example, okay? We have this. Okay, we have this component. Okay, this bromo alkyl. Okay, we have the bromide here. Which who will eliminate? Which other group we need to eliminate? Okay, we need a hydrogen, one carbon away. That means this hydrogen. Please keep this hydrogen away. This hydrogen will never eliminate because it's in the same carbon than the bromine. Okay? Has to be a hydrogen, one carbon away. This is the carbon of the bromine, means that has to be here. Okay? Then, we need to do, I tell you that this will be a E2 elimination. Okay? What we need to do? The first thing that we need to do is to put these two groups in antiperiplanar, 180 degrees, or one up, one down. What I will do is I will rotate this carbon 180 degrees. I am not doing anything chemical. I am only transforming this, moving this into the transition state that I will need to do this reaction. Okay, this remains the same. Okay, and then if I rotate this 180 degrees, I have the hydrogen here. The ethyl that is inside will be in front. Now, please, if you have any problem to do this rotation, use molecular models. Okay, it's very easy using molecular models. And the methyl will be inside. Yeah? Okay, I did this, and now I have the hydrogen and the bromine in antiperiplanar, one up, one down, 180 degrees, as you want to see, as you want to say. Okay? And now what is happening is the reaction takes place. The base is coming, is taking the hydrogen, this pair of electrons is forming the double bond, and the bromine is taking the electrons to depart. And now is the important thing. This reaction, because the transition state is well defined, is stereoselective. What means this? That when we draw the transition state, the elements that are in the same side of the slide will be in the same side of the double bond. We have the double bond here. Which groups are in the same side of the slide or the whiteboard? The phenyl and the ethyl are coming to us, isn't it? Are in the same side. That means that because the phenyl and the ethyl are in the same side, will be in the same side of the double bond. While the methyl is going inside of the whiteboard and the hydrogen is going inside of the whiteboard. That means that both are in the same direction, both will be in the same side of the double bond. Okay, methyl and hydrogen. That means that the only double bond that we will have is here, where the ethyl and the phenyl are in the same side of the double bond. That means that we will have a Z. In this case, we will have a Z double bond. Okay? That means if we have I2, what we need to do as a summary? We need to put the transition state where the hydrogen and the leaving group are in antiperiplanar, 180 degrees, one up, one down, okay? And then the only that we need is to do the reaction, and then we need to be careful that the substituents that are in the same side of the whiteboard, are in front or are behind, are in the same side of the double bond. And that's all. This is an E2 elimination. There are no more secrets. Okay? What we need to do or to practice is basically rotate atoms in order to put the right transition state. And this is the most important. We have a transition state, the reaction is stereoselective. This is very similar to what we did with the SN2 reaction. Very, very similar. Okay? Good. Then, now we will talk about the E1. What we said about the E1? The E1 is basically what we did is that first the leaving group is departing, Okay? We generate a carbocation, okay? And the next step, the base is coming, and what we have is the double one. Okay? That means that two steps. This means that we have an intermediate. That is this guy, the carbocation. If you remember, the first step, the formation of the carbocation, is exactly the same than the nucleophilic substitution unimolecular. Okay? And again, which is, of these two reactions, which is the fast reaction? The fast reaction is the second one. That means that the rate determining step, the step that defines how fast is the reaction, is the first one. If we do this, basically what we have is that the rate of the reaction, it's only depending of the concentration of the starting material, of this guy here. This is why it's called elimination unimolecular. The same that the SM1. And this reaction, we will put an example. Okay, we can put this example. How it's working? First, the leaving group is departing, and we generate this carbocation, okay, and then the base is coming, taking the hydrogen, the pair of electrons that are forming the carbon-hydrogen bond is forming the double bond, and what we get is the final compound. Okay? Now take care that there are no stereoselectivity. Why? Because this carbocation makes that this hydrogen has free rotation in the intermediate. Okay, that means that we can get any double bond. Normally we will get the most stable double bond. That means that we will get the one where the substituents, the big substituents, are more far away of the order. That means the most common result is that we get the E double bond. But we cannot we can get all the possible double bonds. Okay? For example, if here in this phenyl we have a proton, for example, what we will get is we will get these two, the Z and the E, which will be majoritary. Normally the E, because is more stable thermodynamically. Okay? What is the main difference between E1 and E2? E2, transition state, steric specificity. E1, we have an intermediate, 2 steps, carbocation, and we can get a mixture. We will get a mixture of products that, if you remember, is quite similar to the nucleophilic substitution. In the SN2, the product is with inversion of the configuration, while in the SN1 we have a racemic because the carbocation is planar. Okay? Right? Good. And now we will go to the E1CV. Okay, what we said about the E1CV is basically when the base is taking the hydrogen this is the first step. We form the carbon ion, and then after a while the leaving group is departing and the negative charge is forming the double bond, and what we get is the double bond. Okay? This is the process. Okay? In the E1 we said, that is very similar to the SN1, and the reaction works better, E1, when we can stabilize the carbocation, the same as SN1. Okay? Here will be the same. If we can optimize, stabilize the carbon ion, this reaction will work. If we cannot stabilize the carbon ion, this reaction will not work. And how we stabilize a carbon ion? Well, the easy thing is to have an electron with grabbing group in alpha position. That means, for example, a carbonyl group or a carboxyl group will stabilize a carbon ion in the alpha position. Remember that in this case the base is taking the hydrogen, we generate the carbon ion. Okay, why is it stable, this carbon ion? Because we can draw a resonance structure that stabilize the carbon ion. Okay, this is the reason why this hydrogen is slightly acidic, because the carbon ion, the resulting enolate, we can stabilize by resonance form. That means that we will need always to have a group that can stabilize carbon ion. That means that the typical E1CV will be compounds with this structure. Okay? And we will do it. We have the hydrogen here, we add the base, and we generate this compound, this anion, that is stabilized by resonance. Okay? It's stabilized by resonance, this anion. the most reasonable resonance forms is this. But I really prefer that at this level you grow it with the negative charge on the carbon, because if you grow it in the negative charge with the negative charge on the carbon, this explains easily all the chemistry that we will see today and in the next days. Okay? That means if you want to grow both, it's okay. If you want to grow one, it's okay. You have to know that that this is acidic because we can stabilize the negative charge by resonance form, but you can grow the resonance forms that you like more. Okay? And then, what I said is that basically, this is forming the double bond and the leaving group is departing to generate this double bond. Yes? What is the strength of this reaction? The strength of this reaction is that the leaving group is an hydroxy. And what I said to you in the first lesson, that hydroxyl groups are a very bad leaving group. This is the exception. Okay. The OH in the E1CB is a very good leaving group. It's the only case. You cannot use an OH as a leaving group in the SN2, in the SN1, in the E2, or in the E1, because it's a very bad leaving group. It's only good if we are doing a E1CB. Okay? And the final product, normally, we get the most stable, if it's possible. Okay? That means the double. Okay? Then, which is the most important thing of the E1CB? We take the hydrogen first and we form a carbon ion. This is very similar to the E1, but just the opposite. In the E1, what we have is that the leaving group is departing, and then we form a carbocation. Here we form a carbon ion. And then the leaving group is departing after a while, and the reaction takes place. Okay? And the most important is that we need to stabilize the carbon ion. If we cannot stabilize the carbon ion, the reaction cannot take place by E1CB. Okay? That means that we need, for example, a carbonyl group that stabilizes the carbon ion. And in this type of reaction, the most common leaving group, almost always, is a hydroxyl group. That is very good because if we have a hydroxyl group that is leaving, is departing, means that we are doing a E1CB, because if not, we cannot eliminate OH, because simply it's not a good leaving group, except in the E1CB. Okay? Only a fast remember, if we want the hydroxyl group is a good leaving group, what we need to do, to protonate it, and then the leaving group is water, that is a very good leaving group, and then the reaction will take place, the E1, the E2, the SN1, the SN2, whatever we are doing. Okay? But the OH alone with a protonation is not a good leaving group, only in the case of E1CB will work. And that's the summary of the chalk and talk summary for the elimination lectures. If you have any question, feel free to send me an email and I will answer as fast as possible all your questions. Thank you very much and see you soon.